very good morning, my dear students. I hope everybody is doing good. Let's continue the chapter called Alternating Current, right? So what was the chapter? Alternating current. In this alternating current, we had finished average value of current and RMS value of current, my dear children. Average value of current we have done and RMS value of current also we had finished. Now the topic of interest is, listen to me carefully. There is an alternating current source. Carefully see. There is an alternating current source. When this alternating current source is connected to a resistor, what happens to the instantaneous value of current and the EMF? We know generally, so in generally instantaneous EMF is E naught sine omega t. Instantaneous current is I naught sine omega t. Yes or no? So these two values I can say the instantaneous values. Yes or no? It's yes. Those are the general expressions. When you connect an AC source to your resistors, how about the instantaneous values of EMF and current? When you connect this AC source to an inductor, right? Inductor, resistor will opposes the flow of current, inductor will opposes the change of current passing through that. Okay, this opposes the flow of current and this opposes the change of current, right? And when this AC source is connected to the inductor, what happens to this instantaneous EMF and the current values? When this AC source is connected to a capacitor, the same thing, what happens to the instantaneous EMF and the current values? So that's the topic of interest today. In the later classes, what we'll be doing is, when this AC source is connected to a circuit where both resistor and inductor is present, when we connect this AC source to a circuit where inductor and capacitor is connected, what happens to instantaneous EMF and instantaneous current values? When this AC source is connected to a circuit where all the three elements are there, resistor is there, inductor is there and capacitor is also there, okay, what will happen to this instantaneous EMF and the current values? That's our topic of interest today. Alright, clear? Now let's begin the concept with when AC source is connected to the resistor, right? So when AC source is connected to the resistor, what happens? Let's check. So there is a resistor is connected here of resistance R and the source voltage is AC. Carefully see. So this will have some instantaneous EMF E, which is equal to E naught sine omega t. No confusions at all. Now imagine at this instant, I am talking about at this instant because sometimes the current flow clockwise direction and sometimes in anti-clockwise direction in the circuit, because the frequency of this alternating current is 50 Hertz, 50 oscillations in 1 second. In 1 second, 100 times the direction of current is reversed. So that we had already learned. Now at this instant, I am imagining that there is a positive terminal of this battery or a cell, negative terminal of the battery is the other side. So current flow will be here at this instant. So at this instant, so everything, our aim is to find out the things, what changes will happen in the general equations when AC source is connected to a resistor. What changes happens to this equation as well as this equation. Those are instantaneous values, right? At this particular instant, I just wanted to check it here. So let us apply Kirchhoff's voltage law here. Alright. So what is that? From Kirchhoff's voltage law. So current is passing through the resistor in my loop direction. So that is minus I into R. And we are moving in this direction and touch the negative terminal of the cell. So that means this is plus instantaneous EMF is equal to 0. So this I can write E is equal to I into R. So what is E here? So E naught sine omega t, which is equal to IR. Alright. So this I is keeping here and this R is taken to the other side. That will be E naught by R into sine omega t, my dear students. So this E naught by R, I can write it as I naught. Okay, so what I can write, so I is equal to I naught sine omega t. I is equal to, this is I naught. Okay, its values are I naught. I naught is the peak value of current. E naught is peak value of EMF. Okay, so I is equal to I naught into sine omega t we have got. And already what is the instantaneous EMF is taken here. So E naught sine omega t. So general equation is as it is. Of course, this general equation we have discussed in case of AC generator. We have got this. So AC generator is a situation, there is a coil connected to the AC source. Okay. So that is nothing but there is a resistor which is connected to an AC source. So that's it. So I and E values we have got. Here comes an important point, my dear students. Is there any phase difference between I and E? Is there any phase difference between I and E? So now the question of this concept is about a phase difference. What is that? About a phase difference. This phase difference is denoted with a symbol phi. You might have learned in your waves and oscillation topics about phase difference. You know what is the phase difference? It's so simple. Phase difference is simple. Phase of instantaneous EMF minus phase of instantaneous current. That is called the phase difference. It's so simple. What is phase here? So this is phase. First, to know the phase difference, you should know phase, right? What is phase? Phase is whatever the angle. Phase is angle. Simple. Phase is angle. So what is the angle here? Omega t. Right? Sin theta. Where theta is omega t. What is sin theta here? Omega t. Both are same. Phase of instantaneous EMF is omega t minus phase of instantaneous current is also omega t. So what is the phase difference here? So can I say in this case, phase difference is 0? Are you understanding this, my dear students? What is the phase difference here? It's 0. What does it mean by phase difference is 0? I'll tell you, listen to me. Phase difference is 0 means, so this is a sinusoidal value and this is also a sinusoidal value. So I can say the current values are changing according to the sine function. EMF values are also changing according to the sine function. Right? What exactly meant by the phase difference is 0, I am telling you now, you see. When this is a sinusoidal function, this is a sinusoidal function. When the phase difference is 0, so both reach a maximum values at the same time. Understanding? Both reach the maximum values at the same time and both reach the minimum values at the same time and both reach a negative maximum values at the same time. So that's called the real meaning of the phase difference is 0. The real meaning of what? Phase difference is 0. Understand? When there is a phase difference, both will not reach the maximum and minimum points at the same time. One quantity will reach the maximum, another quantity will be lagging behind or leading it. Okay? Clear? Simple. let us concentrate on the resistor only. When an alternating current source is connected to the resistor, we are discussing now. Our instantaneous current and instantaneous EMF values we have got here. Phase difference is 0. Okay, phase difference is 0. And let me draw the phase difference is 0 graphical representation here, right? So that is what the graphical representation I'm just going to explain. So this is time, and this y-axis may be induced, maybe the induced instantaneous EMF or the current, both, anything. We know E is equal to E naught sin omega t. So this is the graph of what? Of E. So imagine this is E naught, my maximum peak value of EMF. So this is the peak value of EMF. Now the interesting part will come here. E is equal to E naught sin omega t graph is done. I is equal to I naught sin omega t. So which is greater? I've told you so many times, E value is greater than I because I is I naught. I naught is what? E naught by R. The whole function is divided by R, then you got this one, right? So when this function is divided by resistance, then you got this. So that means this I value is less. The first class of alternating current we have discussed. So, but even though the I value is less, but phase difference is 0. So that means what? Both reach maximum values at the same time and both reach minimum values at the same time. So now carefully see, both starts at the same time also. Okay. So this is the current values are following the E. Current values are following the E. It's so simple, my dear students. You can see both are starting from 0 and this is the I naught. Okay. So the magnitude of the I naught and magnitude of the E naught is differs. I naught magnitude is less than E naught magnitude. Right? Peak value magnitude is different. So but interesting thing is, this is the time instant, for example, at the time t1, what happens? So there is a peak value is reached by both. I naught is, current is reaching its peak value and EMF is also reaching its peak value. So that's what the phase difference is 0. So both reach maximum values at the same time. Both reach minimum values at the same time. See here. So this is the time t2 where both current and EMF values are reaching to the 0. And this is the time t3. Carefully see, my dear students. This is the time t3 where negative peak values. The same instant, both the functions, both the current and instantaneous EMF values are reaching to the negative peak values. That's called the phase difference is 0. That's called the phase difference is 0. Do you understand? Clear? Sure? This is the concept of phase difference. Understand? No need to go back and refer the waves and oscillations topic even now. It's not required now because we have covered here what exactly the phase difference is here. Okay? Clear? So whatever the angle is here, that's called the phase. The phase difference is difference between two physical quantities here. What are the two physical quantities here? So EMF and current. That's it. Okay? In this complete concept called when AC source is connected to resistor or inductor or capacitor, or when AC source is connected to resistor and inductor, or when AC source is connected to inductor and capacitor, or an AC source is connected to all the three elements in the circuit, whatever may be the topic, we are dealing with a concept called phasor diagram in this chapter. What is that? Phasor diagram. So simple. Phasor diagram. So most of the students will have confusion on this phasor diagram, but you should never have. Because the easiest method, understanding the phasor diagram we are discussing now. Look at these functions I and E. Look at the functions I and E. Both are sinusoidal, right? Any quantity varying sinusoidally, it can be represented. So the motion of it, that means that the variation in these values can be represented with the projections of a uniform circular motion. What is that? A uniform circular motion. What exactly meant by the projections of uniform circular motion? I'll discuss. Don't worry. Listen, one second. Our topic is phasor diagram. What is this phasor diagram? Is any physical quantity is varying its value sinusoidally, you can represent the changes of that physical quantity by using the projection of uniform circular motion. Right? What is the projection of uniform circular motion? And let's have a look at here. I have an x-axis here and a y-axis here. So simple. X-axis and y-axis is here. Imagine this is what the uniform circular motion example. In this uniform circular motion, there is a radius vector. Okay. Imagine this is the radius vector, right? This is the origin and this is the radius vector. And this radius vector is this one. This is the radius vector. That radius vector is called phasor. Understand? So what is that? A radius vector is called phasor. No confusions. This phasor can be represented with an voltage, can be represented with a current. Simple. This radius vector is a rotating vector, right? This radius vector depends on the motion of the particle. So the radius vector will be rotating. Radius vector is also the position vector here. Okay. So this radius vector is also called rotating vector, which is also called a phasor, and this phasor may be represented with a voltage or current values. Imagine already in anti-clockwise direction, so this radius vector is rotated how much? Some angular displacement which is omega t. Yes or no? Yes or no? It's so simple. From the initial position, this radius vector is taken some angular displacement, theta is equal to omega t. That omega t is here. No confusion. That omega t is here. Now, imagine this is the radius vector is represented the voltage OV. And you know this length of this radius vector is represented its magnitude. That's called peak value. The length of this radius vector is representing its peak value. So that is V0. This is V0. Okay. Now, and this V0 will have its own, this V0 radius vector will have its own projections on the x-axis, will have its own projections on the y-axis, and concentrate on the projection of y-axis, right? Projection of this vector on y-axis is how much? So that it is omega t, right? Theta is omega t. So this is the projection, or this is the component is with the theta. That means adjacent to theta. This is sine component and the other component is cos component. So sorry, this is cos component and this is sine component. So this will be V naught sine omega t, and for our better understanding, so let us write this is E naught, because voltage we are keep on carrying with a symbol called epsilon, right? Let's continue with epsilon only, no confusions, right? E naught. Projection of this radius vector on y-axis will be E naught sine omega t. So this is a phasor diagram of voltage. Current phasor diagram also you can draw the same, right? Current phasor diagram. So imagine this is the current and the peak value of current is here. This is I naught, and this phasor vector will also have its own projections on the y-axis, right? So that is I naught sine omega t. This is the phasor diagram. So simple. What is the phasor diagram here? Phasor diagram is any graph or any physical quantity which is varying sinusoidally its motion can be represented with the projections of uniform circular motion. So this phasor vector, this phasor or radius vector will be moving in anti-clockwise direction. That is the initial sign convention you need to take, right? So this is the so simple concept. And by using this phasor diagram, the phase difference can be identified easily. Phase difference can be identified easily, right? Look at here. So this is the E, instantaneous EMF and instantaneous current are in the same phase. You can see the same line. Same line. So same line is represented like this also. This is E, right? So in case of AC source is connected to your resistor, so this is your E and this is your I, right? Phase difference. So for your better understanding, I value will be little less, right? So this is your I. So this is when AC source is connected to the resistance, phase difference is 0. And this is the phasor diagram for that. And here how we have derived the phase difference is 0 and I and E epsilon values. So let's concentrate on the power consumed by the resistor in this circuit, right? Power consumed concept. Power dissipated by the resistor. So let us look at the similar diagram what I have drawn when AC source is connected to the resistor as the positive terminal, negative terminal, and the current is passing through this. We have the power consumed by this resistor, so P is equal to I square into R. This is the basic formula. Here an interesting thing, let's concentrate on instantaneous power consumed, right? So when I write instantaneous power consumed, so that will be I value, instantaneous current value is how much? I naught square sine square omega t, because that is I square, into R. So this I can write it as I naught square into R into sine square omega t. So that is instantaneous power consumed in the circuit. What is that? Instantaneous power consumed in the circuit. Now let's concentrate on for a full cycle. Okay, for a full cycle, let's concentrate on finding average power value, students. Average power. We have the formula to find average power, which is equal to integral power is a function of time divided by integral dt. As it is for the full cycle, it is 0 to t and 0 to t. I hope you could remember this. So that is integral P. Instantaneous power is how much? I naught square into R sine square omega t divided by, so integral dt is t. Okay, so the limits also apply t here. So this is 0 to t. Here itself, I naught square by R divided by t, right? So integral 0 to t is sine square omega t dt. Did you remember the formula of integral sine square theta? Right? Integral sine square theta formula. Sorry, before that sine square theta formula, you know. Sine square theta formula. Sine square theta formula is 1 minus cos 2 theta by 2. Did you remember that? Same, let's apply here. So the average power we are discussing, which is equal to, look at here, I naught square R divided by T. Integral 0 to T full cycle, sine square theta is 1 minus cos 2 theta, theta is omega t, by 2. So into dt. So this is the full. Let's take out this 2 also here. So average power is equal to I naught squared by R into 2t. Here 0 to t integral 1 dt minus, so this is the complete bracket, let's keep, 2 is already taken out. This is integral 0 to t. It's cos 2 omega t dt. Alright. Now, so P average is equal to I naught square R by 2t into, so integral dt is t. The complete value will be 0. You can also check. Already we discussed in detail in case of while finding RMS value of current, right? This is the complete value will be 0. This complete value will be equal to 0. If you want, you can check it. So then I can write, this is finished. T cancel. Right? So what is the average value of current? I naught square R by 2. So that's average value of current. Remember, our average value of power. Average value of power is I naught square R by 2. Okay, average value of power. Now the interesting thing here, instantaneous value of power is this one and average value is this one. Let's write this average value in terms of carefully see, average value in terms of RMS current. We have IRMS is equal to I naught by root 2. So let's square this. IRMS square is equal to I naught square by 2. Right? So what is I naught square? 2 into IRMS square. So the same thing. So I am writing average power is equal to I naught square means 2 into IRMS square into R divided by 2. So look at here. What is that? Average value of the power is I square RMS. Understand? The same average power consumed you can write in terms of ERMS because I is equal to E by R. So when you write this is IRMS and this will obviously it is ERMS. From here resistance is equal to ERMS by IRMS. No further confusions, my dear children. So P average is equal to I square RMS into R. R is ERMS by IRMS. IRMS cancel here. So the average power consumed in a resistive circuit, what is it called? A resistive circuit is equal to ERMS into IRMS. Okay. So all these are, so there are three expressions you can see. Average power is I naught square R by 2. Average power is I square RMS into R. Average power is equal to ERMS into IRMS and whatever it may be. So this one and this one, right? All these things are average power consumed. What is that? Average power consumed in a resistive circuit. What is it called? Resistive circuit. That means when an alternating source is connected to a resistor. So this is what the average power consumed. And listen to this, students. Now in a resistive circuit, what all the things we have discussed? We checked, is there any phase difference between I and E? Then we draw a sinusoidal graph for I and E, right, in the same way. So there itself you can understand whether there is a phase difference or not. And phase diagram also we have drawn for this resistive circuit. The three things we'll be doing for the next concept also. What is the next concept here? When this alternating source is connected to an inductor, when an alternating source is connected to what? Inductor. What happens when an alternating current source is connected to inductor? We'll check whether there is a phase difference between I and E. We'll draw the sinusoidal graphs for I and E, and we'll draw the phase diagram also for I and V. Alright, so then we will check the power dissipated by the inductor. Understand, power dissipated in the inductive circuit. We'll do it now. Well, my dear students, so let's continue the topic called when alternating source is connected to the inductor, right? So let's see. When alternating source is connected to an inductor. So let's have a look at it. So imagine this is the inductor. You know what the inductor does. So alternating source is connected to it. And you know this alternating source voltage is E naught sine omega t. Inductor will have an inductance L. At this instant, I am imagining that there is a growth of current I. When there is a growth of current, this inductor will oppose the growth of current in this way. So that means the induced EMF will be developed and it is a virtual cell or battery of positive and negative terminal. This is everything we have discussed already. Inductor will opposes the change of current. Here the change of current is growth. Now if you carefully see here, this E is equal to L into di by dt. We know this cell. A negative sign is already represented with this cell. No confusions. Let us apply the Kirchhoff's voltage law here also. My loop direction is this one, and I am moving to the, like in this way, touching the positive terminal. Positive terminal I am touching, that means it's minus induced EMF, and I am moving like this and touching the negative terminal here, so that will be plus E naught sine omega t, which is equal to 0. No confusions. So E naught sine omega t is equal to E. What is this E here? This is L into di by dt. Now let's equate this. E naught sine omega t is equal to L into di by dt. This I can also write it as E naught by L into sine omega t, which is equal to into sine omega t into dt, which is equal to di. Both sides, if you integrate, carefully see, if you integrate both sides, what happens? Let's have a look at here. Integral di is I, right? Epsilon naught by L is constant, and here integral sine omega t into dt. There is no concept of limits is applied here. I is equal to epsilon naught by L, integral sine omega t will be minus cos omega t divided by omega. So I is equal to minus epsilon naught by L omega or omega L. In most of the books it will be omega L, no confusions. That is why I wrote omega L into cos omega t. Alright, again I is equal to minus epsilon naught by omega L. This is cos omega t. I am writing it as sine 90 minus theta. Okay, because our current value need to be in sine thetas, because I told you phasor diagrams you can apply any physical quantity which is varying its values instantaneously. Whereas our induced EMF, we have instantaneous EMF we have got in sine function, so that is why current also will keep it in sine function. So that's why I wrote cos theta is sine 90 minus theta. Now this I can also write I is equal to, when negative sign goes inside, so that will be E naught by omega L into sine omega t minus pi by 2. Okay, right? Sine omega t minus pi by 2. Understand? Previously it is sine 90 minus theta. Now it will be sine theta minus 90 because negative sign is kept inside. So now this I is equal to I naught sine, carefully see, omega t minus pi by 2. And if you compare these two equations, we have I naught. Look at here. We have I naught here. I naught is E naught by omega L. In the last session, that means in the last slide, what we have discussed, in case of when AC source is connected to a resistor, our I naught is E naught by R, where R is the resistance in that circuit. In this circuit also there is a resistance, yes or no? When there is an inductor, there is a resistor, right? When there is a resistor only, there won't be any inductance. When there is an inductance, there must be a resistance. So that is what here also you can write. What is that? I naught is equal to E naught by omega L. Carefully see. When you compare these two equations, resistance and here also resistance. Resistance in the previous slide and resistance in this slide. That means, so this is the resistance in this inductive circuit. What is that? Resistance in the inductive circuit. So now from these two expressions, I can write it as I naught is equal to epsilon naught by omega L, which can also be written as epsilon naught by x suffix L, my dear students. And this x suffix L is equal to omega into L, that is called 2 pi frequency into L, and this is called inductive reactance. What is it called? No confusions. Inductive reactance. X suffix L is called inductive reactance. And the numericals will be asked in this way. They give F and they'll give L. The frequency they'll give, and L. Inductance they'll give in terms of Henry. You need to find the inductive reactance. And this inductive reactance units, you get it in ohms. That's an important thing, right? So this will be units, you get it in ohms because it is similar to the resistance only. SI unit of resistance is ohm. Okay. Keep it aside. So this is, keep it aside. And the interesting thing I'll show you here itself. This inductive reactance is depending on the frequency when L is constant. This inductive reactance is depending on L when frequency is constant, remember. Directly proportional, right? When L is constant, so this inductive reactance is directly proportional to frequency. When frequency is constant, inductive reactance is directly proportional to L, right? So graph will be directly proportional like this. So this is the graph. Imagine it's inductive reactance, it is a frequency. So when L is constant. So this is the inductive reactance, and this is L when frequency is constant, directly proportional. Forget about this part and come back to our equations. Our major aim to understand this alternating current is connected to inductor is how the current and EMF values are changing here. Look at the two important expressions I have got here. This is the actual expression. Already we have this expression, right? This is the source voltage here, E naught sine omega t. And this is the current value I have got, instantaneous current in this case. So now let's concentrate on the phase difference, right? So phase difference, let us concentrate. And the phase difference is equal to, right? So let me write this. Phi is what? A phase difference. Phase difference is phase of E, which is omega t, minus phase of I. Phase of I is omega t minus pi by 2 So this will be omega t minus omega t cancel and minus of minus plus. So plus pi by 2 is the phase difference, my dear students. What is the phase difference here? Plus pi by 2. Anyway, it is plus or negative. We take it as magnitude only. Okay, we take magnitude. So anyway, here we got it as plus pi by 2. So phase difference is pi by 2 means what? There is a phase difference. When there is no phase difference, both I and E values are reaching maximum at the same time, minimum at the same time, and reaching 0 at the same time. But in this case, there is phase difference. Phase difference of how much? 90 degrees. Phase difference of how much? 90 degrees. Okay, clear? And this phase difference of 90 degrees, how can you draw? So that's the important thing, right? How can you draw? And before moving to that, look at this. Sin omega t minus pi by 2. So that means this is minus, right? Sin omega t minus something. So what I can write by looking at this, current is lag behind EMF by pi by 2. Okay. So the current value is lagging. See, omega t minus pi by 2. Here, omega t. Okay. Current value is lagging EMF by pi by 2. Or EMF is leading the current by pi by 2. No confusion. Both are same. Right? Current is lagging by pi by 2. EMF is leading by pi by 2. Because for this, if you add pi by 2, the same thing you get. Right? For this, if you subtract with pi by 2, you will get the same thing. Okay, remember any one way. So here as minus pi by 2 is here, current is lagging behind EMF by pi by 2. In where? In alternating source is connected to inductor. Okay, so now here, so let us draw this sine curve. This is EMF or current and this is time. Okay, so simple. My EMF graph is so simple in this way. So this is my E naught and this is my minus E naught. Current now. Current is lagging. Yes or no? Lagging of minus pi by 2. So that means current value is starting from the negative side. Look at here. Right. What happens when EMF is 0, current value is minus peak value. When EMF is peak, current value is 0. When again EMF is 0 and the current value is reaching to the peak value of positive. When EMF is maximum and the current value is reaching to 0 in this way. Look at here once again. When EMF is 0, current value is reaching to the negative maximum. When EMF is reaching maximum, current value is reaching to the 0. It followed in this way. It goes in this way. Right? So this is what the concept behind the phase difference. You can see here when the EMF is 0 initially, but this is starting with a negative peak value. So that's called current values are lagging by pi by 2 angle, phase angle. Okay. Phase diagram, how you can draw. Phase diagram. Simple only. This is x-axis and it is y-axis, alright. If you write, this is your E naught, this is omega t, right? Now your I naught is lagging behind pi by 2. Simple. So this is your I naught and the angle here it is pi by 2. See here, I naught is lagging behind. So current values are lagging behind. Alright. So this is omega t and this is omega t minus pi by 2. See, omega t minus pi by 2. Okay, clear? Now, in simple way, you can also like this. You can take two axes, and this is I values and this is E values. This is a pi by 2. When E is here, so current is lagging behind pi by 2. And you can also do like this. So this is E and this is I. Here also the same thing, right? We take it in anti-clockwise direction, always remember, anti-clockwise direction. When E is here, current is at pi by 2. Okay, lagging behind pi by 2. Everything we take it in anti-clockwise direction. Clean, no confusions. Alright? Clear, my dear students? Now, so before you already, I hope you understand this. So, how and why I wrote this is in case of when AC source is connected to the resistor, this was the situation, right? There's no phase angle between them. We wrote like this. Or you can also represent like this. This is the previous one, but this is now. Alright. So let's solve some numericals, and when AC source is connected to the capacitor concept in the next class. But in this class also prepare for your assignment. There may be some basic numericals related to the power dissipated in the resistor case with the formulas, you know. I told you average power formula, average power in terms of RMS current, in terms of RMS voltage, right? There may be questions based on that, and there may be a question based on this also, and these graphs and these phase diagrams and these sinusoidal graphs and these phase diagrams. Okay, so be prepared for this. And then before going to the assignment, let me tell you one important thing here. Average power associated in this case for a full cycle is 0. For a full cycle is 0. Derivation is not required for us. If you want the derivation, you can do that. How? We have the power expressions. Power is equal to E into I. So whereas E value, instantaneous, I am talking about instantaneous. Instantaneous E value is here. Instantaneous current value we have got here. Okay. So you can take this like this. Instantaneous EMF, you know, instantaneous current also, you know. This is instantaneous power, and use the average power, which is integral of instantaneous power into dt divided by dt. So integral 0 to total time t, and you do that, you get the average power as 0. Remember, in an inductive circuit, average power consumed is 0 for a full cycle. Okay. But resistance, it's not like that. There are 3 expressions we have discussed. Fine. Get ready for your assignment.